Okay, and so I'm thankful to the organizers for giving me this opportunity to share my thoughts on reinforcement learning as related to model predictive control. And I gave this very similarly titled talk at the World Congress, IFAC World Congress last year. That was about 10 months ago, right? So not a lot has happened since then, at least on the theoretical front. So this will be more of an abridged version of that talk. But what happened since then was that I've been working on a number of industrial projects that uses machine learning for optimization. And so, what I'm gonna speak today, even though maybe same story, I'm speaking with more practical perspective and conviction than before. And so what I want to do is I want to explore the potential of reinforcement learning for replacing it or complementing model predictive control in the context of solving optimal control problems for process control applications. So first of all, a bit about machine learning that most of you know. There are large three branches, as you know. There's supervised learning, learning between X and Y data, regression classification, or fit into this. Unsupervised learning, where you have unlabeled data, you want to kind of learn the distribution of data, clustering, dimensionality reductions through autoencoding and things like that. And then there's the reinforcement learning, which combines the former two with optimal decision making in a dynamic environment. So it sort of combines optimization with sampling. It involves the decision of sampling. That's what's unique about reinforcement learning, that it involves the decision of sampling as well as optimizing an objective function in a sequential manner. So while unsupervised and supervised learnings are passive learnings, that is, they try to learn patterns with given data, reinforcement learning is active learning in the sense that it performs the task of data sampling simultaneously with optimization. It's optimizing the whole process so that the best new patterns can be generated for the optimization task. In that sense, it's a complete kind of story. If you look at human learning as kind of learning for and decision making repeated, I think to create something that's close to human, you have to address the issue of reinforcement learning. And this is particularly relevant in data-based optimization, where a lot of industries are interested in this. So the difference would be that the supervised learning will try to take the given data and construct a model and then try to optimize within the region of the data. Of course, with deep neural network and so on, you can hopelessly overfit the data, and there's always caution that one has to exercise with that. Okay, but the reinforcement learning, what it'll do is it'll try to explore into a region that hasn't been tested, so they can find a better optimum or even global optimum. Okay, so that's very relevant in the context of, I think, data-based learning. But admittedly, most industries are very uncomfortable with online learning and active learning. That most of them would like to do the former, which is constructing model with given data available offline and then do optimization. To me, that's very dangerous because you can easily overfit and come up with some senseless result. Okay. The only project where I was involved in this active learning was material design. So I've done this one project with industry on material design where you're trying to explore in the material space, and that was very useful. And in that context, reinforcement learning is kind of a generalization of what they call Bayesian learning or Bayesian optimization. Okay, so you know all the story about this AlphaGo and how that captured the world's attention. That's basically prime example of reinforcement learning because it's a Go is a notoriously difficult problem for computers due to its combinatorial complexity. And it used deep neural networks for value and policy functions so that the depth and width of the search can be reduced significantly. So that's how it did. It reduced the depth and width of the search using the idea of reinforcement learning as well as deep neural network. And of course, it had this advantage of tremendous computational power, played 30 million games against itself while learning. And also another thing is the problem was a very good fit for reinforcement learning because even though it was combinatorially complex, the transition rules of the game, evaluation rules, and so on were clearly spelled out. There were no uncertainties regarding that. It's only the opponent's play that was uncertain. So you could carry out very realistic simulations, a lot of them, right? So the purpose of this talk, let's talk about reinforcement learning's potential for optimal control. This is the standard optimal control problem. The current method would be model predictive control, also called receding horizon control, where you compute the optimal trajectory, open loop trajectory numerically for a given state at each sample time online, and you repeat this. Now, reinforcement learning provides an alternative or complementary method for solving this optimal control problem, and it has been, developed, at least in certain community, as a way of approximately solve a dynamic programming problem, which is another way of constructing optimal control policy. Okay, so sometimes it's called approximate dynamic programming, neurodynamic programming, heuristic dynamic programming, and so on. And also it's called active critique method. Okay, so the question is if you're gonna adopt reinforcement learning, because model predictive control is very well established in the process industry, it's gotta offer something extra, right? I mean, if it does only as well as MPC, there's no reason to replace MPC because MPC is doing very well. What are the pros and cons? What's the advantages, disadvantages relative to MPC? Also, better, can you combine the two in a complementary manner? So let's examine those questions. Okay, so the outline is we'll talk about MPC, we'll talk about RL, then we'll talk about their relative merits and see how they can be how they fit into process control context. So optimal control problem that we study here, which is what I have written is for the finite horizon optimal control problem, subject to some dynamics, like given the system of ODEs. So sometimes you can use DAEs as well. And VT is called the value function, which that's an important term in reinforcement learning or dynamic programming, which represents the cost achieved on the optimal control. So if you do everything optimally, how much would be the cost starting from this state? So it's a function of state, starting state, and it's a function of time as well. A general solution is given by the Hamilton-Jacobi-Bellman equation that is shown here. That's a PDE because that's a PDE with respect to the state variable. And so boundary condition, you have boundary condition, and so on. So this once you get this value function, then the optimal state feedback log can be easily derived using calculus, right? But analytical solution is seldom possible, right, of this PDE. And then discretizing and solving it will certainly cause exponential explosion with respect to state dimension. And that's referred to as the curse of dimensionality. Okay, so dynamic programming, though elegant in concept, is not that useful in practice. Now, you have the special case here where T goes to infinity, so you have the infinite horizon problem. And in fact, for for this problem, infinite horizon is easier because you get a stationary solution. So you no longer get time-dependent value function and time-dependent optimal control law. You have something that's independent of time. Okay, but that's the HAB equation for infinite horizon, and discrete time index, discrete time case, you have this equivalent kind of a Bellman equation here, which was originally proposed by Bellman. And then there's the stochastic case that involves additional expectation. And if it's continuous time, it's even more calculated because you got to use Ito calculus, right? But basically, all these problems share the same fundamental problem that I talked about in this standard problem, that curse of dimensionality and so on, no analytical solution. Okay, so HAB equation is not, the solution is now obtainable. So as an alternative, MPC has emerged. So instead of solving the problems entirely offline, you can solve this online for a particular given state at each time. So whatever your state is right now, that will be the starting state. And you can solve it numerically using mathematical programming. That's easier than solving it for the entire state. And as the computing hardware got better and better, and numerical methods, the MPC approach has become a feasible option. Now, it should be noted that even though an open loop optimal control problem is solved, it's actually feedback control law, because only those moves for the current control interval is implemented, and the whole optimization is redone at the next amplifier after feedback. This is called receiving horizon control. Okay. So analogy is this passing of this truck. And I'm sure you've experienced it when you try to pass a truck. Invariably, I think it's human psychology embedded in our evolution, is competitiveness, that truck driver doesn't want to let you pass that easily, right? So he speeds up. So whatever trajectory you had in mind, if you follow that, you're going to crash, right? So you're going to have to adjust as you make the passing. Again, to review, you solve the problem in terms of the input sequence for specific measured state. Now, why is MPC so popular? Why has it succeeded so much? Because of the fact that you can enforce inequality constraints, which is a big advantage in terms of defining control problems, especially in process control. The optimization that you solve is linear, quadratic, nonlinear. Programming, depending on the nature of the model and the objective function. And these solution packages are getting better, right? And there in the 80s, when MPC came out, they were kind of industrial heuristics, right? You do this, you do that, and it kind of works and so on. But a lot of research has been done since then, and there's a sound theory now with horizon going to infinity. You can guarantee closed loop stability, and therefore, how do you mimic the infinite horizon MPC? That has been the key kind of contribution of the theoretical research. I think one of the downside is MPC is that it's an open loop optimization. It's an open loop optimal control, which is implemented in receding horizon way, which means that it only reacts to uncertainties as opposed to proactively planning for uncertainties. If you want to do this, you get into all sorts of like exponential branching, stochastic programming, and it becomes a mess. So even though there are multi-stage MPCs and things like that proposed for better robustness, to me, it's not really extendable to practical problems. Okay, and MPC, as we know, showed up in the process industry. It's very popular to factor the APC method of process industry. Many vendors, now it's all kind of standard. And it's not just the process industry these days, it's also automotive industries, aerospace industries, all using MPC for good purpose. Now, reinforcement learning goes back a long way, actually, with psychologists like Edward Thorndike and mathematicians and computer scientists like Alan Turing. Alan Turing made this remark that, trying to produce program that can simulate the learning of a child. So starting from blank and then gradually learning through experience. That vision of Turing has been realized today, okay, with powerful computing hardware and deep neural nets and so on, and it's threatening human cognition these days. People are worried that you're going to create something that's going to be more intelligent than humans. That humans will become useless, right? They call it unconscious or non-conscious intelligence. Anyways, formally in reinforcement learning, agent learns a map between state and action. So it's a map between state and action that maximizes a long-term value of a function, right? Because it's a dynamic optimization. Usually exponentially discounted because you want to have finite cost value for infinite horizon case. Again, its rich history include trial and error learning from animal psychology to some early works in artificial intelligence. And it has connection with optimal control, obviously, through dynamic programming, Bellman's optimality, and this value function is kind of the common thread. And because the Bellman equation, optimality equation cannot be solved exactly, one tries to conceive an approximate way of solving it. And according to Sutton and Bartow, all our algorithms can be regarded as sample-based approximate solution to Bellman equation. Okay, so interpretation of reinforcement learning is that you try to solve this formal Bellman optimality equation, but in some approximate heuristic way. Okay. So research in reinforcement learning has come from different threads: temporal difference learning, which tries to learn the value functions through bootstrapping, right? So that's like a Q learning and so on. Policy gradient method, where you are trying to learn the policy function directly, skipping the value function. And then dynamic programming thread with effort to approximately solve the Bellman equation, led by people like Dmitry Bersekas, Warren Powell, Paul Werbers, and people like that. But these different threads are all reconciled now, and they form a coherent and unified field of reinforcement learning. And that has been applied a lot in games, elevator dispatching, robotics, navigation, etc. Not so much in process control. Now, I have shown this more than a few times, so let me just quickly go this bipedal robot, and it's a huge, relatively huge control problem, 24 continuous states, and you try to make it learn using DDPG algorithm. That's a policy active reading method, right? And why doesn't it work? Well, maybe it's because I'm using this laser point. Okay, for some reason this animation is not working. But so this is exciting, but will it work for process control? That's the question that we have in mind, right? So for first of all, in most chemical plants, it is very difficult to obtain a huge volume of exploratory data as required by most of these algorithms. They don't want to do like exploration and continuous learning and things like that. That's why adaptive control hasn't taken off, in my opinion, in the process industry. Okay. Second, one could use a simulation model to generate the data, but there may be significant mismatch. Simulation is just simulation. It's not the real thing, right? There's a mismatch, but you could potentially simulate this mismatch as well, right? So you can do simulation if you know where the uncertainties are. If you know certain parameters are uncertain, or you have certain disturbances, and there are statistical nature and so on, you could do Monte Carlo simulations, right? And learn a policy that would be quite robust against that. So it does offer something very attractive because it learns directly from data, and the data could contain various kinds of uncertainties. Okay, and that's also, the theme of this workshop is Industry 4.0. I think at the core of Industry 4.0 is data and things like high fidelity simulation, digital twins and things like that. So, if we are going toward that, then we might as well use that for good purposes, right? Okay, now let's explore or let's discuss this further in terms of how reinforcement learning may be used in process control to complement existing technologies. Now, there's always this talk that, MPC is model-based, reinforcement learning is data-based. So, but to me, both are data-based and both are model-based. Why? Because MPC requires a model, but the model usually comes from plant data. So you could say it's database too. It's just that it's like supervised learning and optimization. Usually you take the data ahead of time and then you fit the model and then you use it for optimization. Okay, reinforcement learning uses data, but they can also come from like very high fidelity simulations, right? So it could work both ways. And then there's this role of system identification. And in the case of MPC, you usually do open loop testing, right? So you have a period where you are perturbing your plan with steps or pseudo random binary signals and things like that. And then you collect the data to fit a relatively simple model, like a linear model. And then you use it to design MPC, and that's it. But that may not be sufficient, and the plans change, right? So the model may not provide accurate prediction in closed loop setting. Feedback will help you overcome some of that, but will not solve it completely, right? So in reinforcement learning, also does a sort of identification, but it's like adaptive control. Learning is done in closed loop over a much longer period, much like adaptive control if the learning is done entirely online. But due to its closed loop nature, the balancing of exploration and exploitation come up, that how much you want to explore versus how much you want to be cautious and exploit the information that you have already. Also, instead of a linear model that's learned in MPC, the value function or policy function, which are usually non-linear, are learned. That's why you use things like neural networks. But you don't have to use neural networks for reinforcement learning. So what are the advantages of reinforcement learning versus MPC? One of the advantages is the modeling can be implicit. So it doesn't not use the model or not have a model, but it may be implicit, like in Q function, certainly, which expresses the value function expressed in terms of the state and action. It implicitly includes the system dynamics, transition dynamics. Another advantage is that it can handle nonlinear stochastic system in a near optimal way, given that enough data are produced through Monte Carlo simulations. So it's more than just reacting to error given by feedback. In fact, it is more robust, actively guarding against future uncertainties and so on, as well as actively reducing uncertainty, as in dual optimal control. Okay. Also, it works with data samples rather than a mathematical model, which can be more general if you think about it, because you don't really need certain form of model like the ODEs and so on. You don't need a declarative model. You just need computational model, sampling model, whatever that can give you data samples through computer simulation. Okay, that's a lot more general. And most of the calculation is done offline and minimizes the online computational requirements. What's the disadvantage? Disadvantage is that you need to do extensive trial and error learning, which may not be feasible for most practical systems, right? So it's not for all applications. It's possible for things like AlphaGo, but not for refineries, for example. The training process is basically non-convex optimization. It may not be stable or repeatable, and that's a problem. That's getting better, but nevertheless, when my students learn it, run this with random seed, usually you give random seed in this learning, and every time they get different results. So that's pretty difficult in practice. Extensive goal engineering is needed, and then whenever goal changes, you must redo the learning. Well, this is like you have some of that in MPC as well. If you're doing explicit MPC, for example, whenever you do offline learning, something changes, you must redo, right? If you are doing online optimization, you may be able to change it on the fly. And it is difficult to provide any sort of theoretical guarantee, but this was the case for MPC as well in the 80s, that it was largely viewed as industrial heuristics, but a lot of research solved that problem. So I expect that the future will also correct this issue. Okay, control-specific issues, process control-specific issues, many problems, many variables, non-square optimization requirements, significant uncertainties, nonlinearity. We all know that. Plus the real plan situation, which prohibits the need of reinforcement learning. Safety, stable operation is of utmost importance. But encouraging thing is dynamic simulations are becoming more widespread, but significant model errors. So if you can model errors, then you can embed that into simulation. Models are often very complex, and so it may be very difficult to use them directly online, and that goes well for offline approaches. Okay, so should we replace controllers with MPC controllers with reinforcement learning? I would not say so. I mean, at least for continuous plants like refineries and chemical plants and so on, I would say model predictive control is so well established, it's going to be very difficult for something like reinforcement learning to penetrate and replace it. It may be able to complement it, make it better. Okay, that's a better way to think about it. But then there are kinds of problems that MPC has not penetrated, like batch process control that Prof was talking about, and I think that's a very good opportunity, especially because it's a nonlinear stochastic problems. So when dynamic simulations are possible, you have a good starting point to use simulation data to build good initial policy, and then you can further adjust it online. Okay, I kind of make an analogy to human learning, right? That most of us do not learn from scratch. Actually, our DNA is optimized through millions of years of evolution to begin with, and then we are educated. Okay, and then you become an effective worker after all that education through on-site learning. So just like that, we shouldn't subject a reinforcement learning controller directly online. Okay, you should use whatever information available and come up with a initially training to come up with a good starting controller, and then you can further adjust it online according to the need. Just as Prof was talking about model migration and so on, all these things are applicable here. And so how do we combine MPC with RL? I think value function can be useful. If you can learn value function offline, you can certainly use it in MPC to shorten the horizon, as well as to provide better robustness, in my opinion, if it's learned with model uncertainty. And model predictive control actually can also help in terms of reinforcement learning offline, because it gives you good starting policy, suboptimal policy, where sampling becomes much more efficient. Now, online, you can also help each other. That the reinforcement learning gives an initial guess for the optimization after a large change. So if you're doing nonlinear MPC, for example, you can get a pretty good initial starting point. And also, model predictive control can serve as a backup when an unexplored state is encountered where you don't trust the reinforcement learning anymore. So they can help each other in this way. Now, one very interesting application, or the opportunistic application you have, is the batch process control. Because if you look at the challenges in batch process control, and I'm so glad that Furong went before me because he explained all this. You experience a lot of these non-stationary, non-linear nature of dynamics. And then you really have emphasis on end product quality. Uncertainties are prevalent, and you have optimization as well as control requirement. Okay, so you have MPC, nonlinear MPC, and economic MPC trying to address that. Iterative learning MPC, we worked on it, Furong worked on it, and so on. But those are useful, but reinforcement learning, I think, adds extra dimension. Okay, so what are issues in designing reinforcement learning for batch process control? Choice of reward function, penalty function. Do you want to do bootstrapping, temporal difference, where you're doing heavy bootstrapping, or do you want to simulate a lot and Monte Carlo simulation and do deep backups? And then do you want to go value-based algorithm, policy-based algorithm, or active critic that uses both value and policy approximations? And so just case study of semi-batch polymerization reactor. This is a polyol reactor producing produced from propylene oxide. And it's a very complex process with path constraints and endpoint constraints and so on. And it's got, it's got 12-dimensional state space, 2-dimensional action space. We're going to assume perfect state feedback for now. And the training data are produced by simulating the model with random perturbations on some of the uncertainties, uncertain parameters, and so on. And one thing is that one lesson is that, as Furong also said, there are distinct phases, right? So there's feeding phase and reaction phase, but there may be a lot more phases and so on. Okay. And the question is, can we really fit one neural network to the entire thing, single neural network? Because then maybe like you're trying to stretch something approximator to do a lot, and you can get into trouble by doing this. So maybe you want to fit different active critic networks for different phases. The second thing is in terms of learning algorithms, you can do, we consider deep deterministic policy gradient, which is an active critic method. Bootstrapping is dangerous here because, if you're doing shallow backup, initially you get a very bad estimate. And the emphasis is at the end of the batch. A lot of important requirements are at the end. So, if initially the value function may not convert because you don't have a very good estimate to begin with. So indeed, you do have to do deep backup to see the end result, to come up with a pretty good approximation of the value that you will get at the end of the batch. Okay. And so we found that the Monte Carlo deep deterministic policy gradient works much better. And that's shown here that, temporal difference DDPG diverged, didn't really do the learning properly. Monte Carlo deep deterministic policy gradient did much better in terms of learning. And compared to the MPC, nonlinear MPC, because of the model error, that it violates path constraints, it violates the end constraints. And if you can incorporate those in the simulation data, in the learning data, we can learn it so that the constraints will be respected despite the model error, and end constraints are also satisfied. Now, a real opportunity related to Furong's example is this batch-to-batch learning and this active learning, okay? That you can, this reinforcement learning can do active learning. It can actually balance optimally the two objectives of exploration and exploitation. So when you have uncertainty, you have to do this. This goes back to dual control concept introduced by Feldbaum. And the question is how to balance it, right? I mean, Bayesian optimization also does that, but in heuristic way. So reinforcement learning does it in much more formal way in multi-stage context. Okay, so you got this batch-to-batch learning. So if you have a product campaign, it usually lasts for a long time, and then you may have a feedstock switch, and it doesn't switch that often. Once you switch feedstock, you may do many runs. So there may be some learning to do whenever this transition happens in terms of products or in terms of feedstock. And so you may actually want to balance exploitation with the exploration here. So let me show you an example of this in the context of biobutanol fermentation. You can show there are 4 uncertain parameters that change according to the feed quality. You got fixed batch time and end product quality and so on. And you can see certainty equivalence where you don't really update model parameters at all. Reinforcement learning with horizon 1, so you don't do any active learning. You are just guarding against uncertainty in this case. And then reinforcement learning with horizon of 10, because you are looking out that there's benefit of trading off between exploration and exploitation, because if you learn now, you will benefit later. Okay, if you do that, you can kind of see you do much better, with active learning. Now, if you look at this reward difference between h equal to 10 and h equal to 1, you actually do worse in the beginning because you are doing active learning that you are not, you're doing more testing in other words. So reward is actually worse than this, but later on your parameter estimation gets much better, right? So you start reaping benefits of these better learned parameters, and you do much better later on. So overall, average total reward is much better. Okay, so let me summarize the reinforcement learning. I try to give you the basic concept and possibly some perspective, industrial perspective in terms of where this may fit in, what it can do. Now, I said it as a continuous system control. I don't think it can just get in there and replace MPC. It can complement certainly, and we have to look for ways of doing that. For other applications like batch operation, you have much better opportunity in terms of starting something, that's entirely new, in my opinion. So I think it has a role. I think the role will be one of complementary nature to enhance the performance and broaden the scope of existing optimal control methods like MPC and AcQG. Some inherent advantages are there, such as the ability to better handle nonlinear stochastic systems if you can simulate it, or if you can do active learning online. But the downside is that you will require a huge volume of exploratory data, either real or simulated. So it may not work well for most real systems. Okay, but that's true for any, I think, database optimization, in my opinion. Finally, I think formulations and alterations suitable for different types of process control problems are needed. Okay, you can't just take these what you read in the literature and directly apply to problems and say, oh, it worked or it didn't work. That's what happened with LQG or Harman filter and so on. You need to really understand the technique and then fit it into the needs of the problem at hand. And I showed that for the example of batch process control. Batch, has a unique characteristics, and you need to kind of tailor reinforcement learning algorithms to the specific traits and needs of batch process control problems. And I think that's what's important, and that's what's needed for research. So with that, I'd like to end, but I'd like to acknowledge the contributions of my graduate students, a lot of whom are attending this. Many of them worked on this, and I'm just reporting what they found out. So thank you, all the LENS members. Thank you for that, and my coworkers, as well as funding agencies like the National Research Foundation of Korea and many companies I work with. Thank you very much.